So I'm going to speak, I've just moved to the US like in February, and I'm consciously aware now that I have like a really thick Australian accent. So if I say something really, really fast that doesn't make sense to anybody, just go, excuse us, mate, and I'll let you know what I meant. So I want to talk today about event-driven configuration. When things change in the environment, how we can update the configuration of things that depend on that using serverless rather than running a service somewhere to, inspect the state of things and update configs. We'll just do it on the fly as things happen. So a little bit about me. As I say, I moved here in February. Currently on the SRE team at Dropbox. Really freaking pumped to be here, actually. It's a bit of a dream come true from little old Western Australia. There's not as much opportunity out there, so I'm absorbing as much Silicon Valley, San Francisco as I can while I'm here, and really, really psyched to meet everyone here. So I've been married for 12 years. I got married at like 20, so very, very privileged to be so. I've got a 10-year-old girl who I brought over with me as well, and one great big Rottweiler. Man, it is hard to get rentals in San Francisco with a Rottweiler, so I may be moving back home again. If you're interested, I read lots of comic books, love to talk about Swamp Thing, love to talk about Batman. I slap a little bass. Dropbox have like a music studio, so so like a bass guitar. Some people play it, I slap it. And yeah, so Dropbox have like this really cool music room where they've got drums and bass and keyboard all set up, and you can just mosey in whenever you like, and I spend most of my time there and collect my paycheck. So, something interesting, I'm currently writing like a Sega Genesis emulator. I used to love the Genesis as a kid, so I'm trying to like rebuild it in Go. I love the Go language. There's no reason to build one. There's really well-performing ones out there already, and mine will be much worse than those, but it's heaps of fun. So, and I respond really well to audience interaction. So, I'm a little bit nervous if you guys just say, hey, that's great, every now and then, that'd be awesome. Thanks, man. All right, so we're going to talk about AWS Lambda as the point solution here, and what I'm hoping you walk away with really is kind of thinking about some of the trade-offs in using AWS Lambda specifically, but serverless, being conscious of the kind of guarantees that you're given. And I'm aiming this talk really at kind of first-time function as a service users. So forgive me if it's old hat to you, but I'm sure it's new to some folks. So I'll first cover the problem statement, like the actual scenario that we were trying to solve in this situation. A little bit about how AWS Lambda works, how we applied it to this problem, some of the things that broke then and how we fixed those, and I've got some time for Q&A at the end. So my previous job in Western Australia was working for a media company who had this massive portfolio of online news sites and video streaming platforms and TV stations and newspapers. And I was responsible I was the engineering manager for the operations team that ran all of the digital assets. So we had an order of hundreds of servers in AWS, and we hosted some sites that had millions of hits per month, which where I'm from is actually pretty freaking impressive, but there's people from Google here, so. We had maybe tens of server roles, so web servers, proxy servers, database servers, and we had to monitor all of this. So at the time, there wasn't sort of any good point solutions for integrating with AWS for like discovery of hosts, and I would like to say it's even pre-Honeycomb, right? So we're going to talk about some monitoring tools that are not Honeycomb and how terrible they are. So our tools were not integrated with AWS. So the tool we used was actually Zabbix. So Zabbix is like this little open source engine that could sort of competitor to Nagios, all in one sort of monolithic solution. You install agents on your Linux machines or Windows machines. They sample metrics from those machines and they ship them to a Zabbix server, which saves them into a MySQL database, and then there's a nice little PHP-driven front end to visualize that data and trigger alerts and etc. So I actually have a fairly big history with Zabbix as an open source contributor. I was honored to be invited to their annual conference and do a talk in Latvia, which is where they are from. And all of that experience and all my open source projects are now like completely stale, that I have a real job, so it's kind of upsetting, but it's good. So Zabbix, the problem we want to solve here actually is how do we, when a new instance comes online in AWS, how do we configure that instance in Zabbix? How do we make Zabbix aware of it, tell Zabbix what metrics to monitor, etc.? So The first option really is that the agent that comes with this tool allows you to do some pattern matching based on like the uname string, right? So it'll run uname, it'll get the system architecture, it'll get the Linux version, and we can sort of just go, hey, if it's got Ubuntu 16 in it, then I'm going to apply these templates. Problem is, it's not very granular. We've got web servers, proxies, databases. It doesn't tell us what it is. That information is in our EC2 tags, and we want to expose that. There's no deregistration, so like when an agent goes offline deliberately, we want it to go offline, we're going to get alerted on that. And there's no alarms for like failed boot. So suppose a machine comes online and never registers itself, then we're never going to be alarmed about that. And lastly, there's no alarms for unreachable hosts. So if a machine comes online and is healthy but is not reachable, we never even start monitoring it. So bad option, basically. Another option is batch sync, and I've done this in the past where we kind of write a script to just interrogate the EC2 APIs and say, tell me all of your machines, and then I'll go interrogate the Zabbix API, and I'll say, you know, what machines have you got, and then we'll create a diff, and then we'll remediate that diff and say, you know, create these hosts, kill these hosts. It works, but it scales really poorly. So, you know, some of the issues are that it's slow, it's all single-threaded, and we have to load up these massive data sets. You know, this great big set of EC2 hosts in both Zabbix and EC2 can consume a lot of memory. So, and it's just unnecessary load on the API. Like while it tries to pull all these objects from the database, transform them into PHP objects, and ship them to the client. The worst thing about this is that you know, same issue as before. If a host disappears from the network, we're going to get an alarm until the script runs. So it's probably going to run hourly or nightly. And there's delayed monitoring for new hosts. So we do get monitoring for new hosts, but it's, you know, it has to wait until the script runs. The old world. So enter the new world. Functions as a service. We can trigger events as they happen and respond to those. Something that's really cool about this is that the scope of the diff, I've said, is limited to just that host. So rather than having to go load up all hosts from Zabbix, all hosts from EC2, we get a little event that says this host has changed, and I can just pull that host and figure out what the diff is. It's a much lighter weight operation. We've got you know, much less resource contention. And the cool thing about functions as a service is they're as a service. So we don't have to worry about the elasticity of it, you know, the scaling it out. If there's hundreds of events that need to be processed, we don't need to worry about availability. These problems are taken care of for us. We pay the check and we get 101% uptime. In a few slides, we'll debunk that. So if you're new to AWS Lambda, hopefully I can make it a little bit clearer for you. It's at first, like, it could be this, it could be that, so hopefully we can make it a little more concrete. Please do read the manual. There's a whole bunch of things I'm going to glaze over in explaining it, namely like how the IAM permissions work and VPC networking configuration. We'll leave those things because they're very unique to your use case, but we'll start with just a really simple Python function, a little hello world handler, which this function takes two parameters. One is the event and one is the context, and then we're going to return hello world. So the event is whatever's happened. We could be triggering a Lambda function by hand and passing a whole bunch of parameters, and they will be available in the event. Maybe it's an EC2 event or an S3 event, and that data will be available in that event object. The context object is kind of the execution context. It's going to contain information about the request ID, how much time is left before the function has to exit gracefully, those sorts of you know, runtime problems. And yeah, let's move on. And we're going to return an object, and that object's going to be printed out to our logs or return back to the caller. So once we have a function, we've got a little Python document with a single handler in it. We're going to need to zip it up to publish it to AWS Lambda. So that zip file needs to be self-contained. So we're going to use, like in my case, pip install to pull in all of the dependent packages into the local directory, and then we're going to zip it up into a self-contained file. So that zip file needs to contain everything that code needs to run, all of its dependencies without exception, with the exception of the AWS runtime, which they make available to you, and the Python standard library. So anything else has got to go in that zip file. And lastly, we're going to publish, and we're going to ship that zip file off to AWS Lambda. There's a whole bunch of ways to do this. AWS CLI, you can write your own client for the API. I highly recommend you use Terraform or a similar tool. But essentially our CLI here is going to publish a new function, a new AWS function called Hello World. We're going to tell it to use Python 2.7. We're telling it the handler to use, which is the function we just wrote in a file named Lambda, and the function's called Hello World Handler, and then the path to the zip file. So pushes it up to AWS, and it becomes available as a function that we can call through myriad different entry points. So to run it, in this case, we're just going to use the AWS CLI to invoke our function, and we're not going to pass it in anything, and it's going to return to us Hello World. Is everyone following along so far? Can I clarify any of that? Cool. Any output is, like if you print to standard out or you use the logging APIs, that information is going to get logged to CloudWatch, where you can trigger alarms on errors and sort of debug any problems that happen. You want to be really verbose with your logs because when that function executes, you can't see it, like you can't tail it. So yeah, it pays to spray. So I mentioned there's a whole bunch of ways to invoke a Lambda or trigger a Lambda function. The primary cause, and the one that we'll discuss today, is event sources. So you can trigger off AWS S3 or DynamoDB or Kinesis. And that is like, by example, a new document's been uploaded to S3, or someone's downloaded something from S3, or a table's been modified in DynamoDB. You can trigger events from those and execute a Lambda based on with that event data. There's also scheduled events where you can just say, like a cron job, I want to run this Lambda expression every 1 or 2 minutes. And finally, there's custom invocation. So you can just literally, as we did with the CLI, just invoke a function right now, or in your custom application, you could use some JavaScript or Python to use the APIs to invoke that function. All right. So that's what functions as a service hopefully generally makes sense, but specifically AWS Lambda is. And as I say, you don't have to worry about the operational side of running this or whether a machine will be available. They're just AWS handle that problem. So next, we are going to create a Lambda function specifically to modify Zabbix configuration. We're going to subscribe to CloudWatch events. Specifically, CloudWatch is, you can't subscribe to EC2 events. It doesn't have like its own event engine, but CloudWatch, which is a tool for monitoring all of AWS, does expose an event engine for changes to EC2. So that's why we use that. And once we've done that, everything's going to be excellent, and there won't be any problems, and we'll just chill like Thanos. You know how like he spoilers. Let's not spoilers. So this is some pseudo Python code for our Zabbix handler. So we've got a Lambda expression that is given an event, and the event is a state change for an EC2 machine. And the only two details we have is the instance ID that changed and the new state. So we extract that from the event, and then we say if the state is pending or running, then we're going to upsert that host into Zabbix. Obviously, there's a lot of logic there that happens in terms of transforming the API object, checking that it doesn't exist already, et cetera, et cetera. Next, we'll check if the state is terminated. If that machine's been terminated, we're going to archive it, right? So we'll stop monitoring, we'll ship all the data off to tier 2 storage, etc. And finally, if it's some other state, we don't know what it is, so we just no op, and we return that information back to the caller. So to subscribe to EC2 events, we're going to create a CloudWatch events rule. Hopefully, we'll leave this for an exercise for everybody to do at home, but if you're looking for how to solve this problem, these are the steps you're going to have to go through. Create that CloudWatch events rule. You're going to have to give it an event source pattern that tells it to look for EC2 state changes. And you're going to tell it the target of that rule. The target is a Lambda function, and we give it the name of our function. And then the data that's passed to that Lambda function is this bottom little snippet here. As I said before, it contains the instance ID and the new state. All right, so now, using this AWS Lambda that we've built, that we've published, that is plugged into both APIs, when a machine starts up, it's monitored for boot issues and reachability straight away, right? Zabbix is aware that it exists, even if it hasn't self-registered, even if it's not reachable, even if it fails to boot. So we can trigger alarms on these scenarios. On termination, we actually get an event to say, hey, this machine's gone. We want it to be gone. You can stop monitoring it now. We don't get any alarms. And then these awkward colleagues clap. So a couple of problems that happen in this scenario is that we end up with missing instances or sort of stale state in the monitoring tool. And the reason for that is we have this scenario in our media company where we would turn up hundreds of hosts daily, mainly for dev, right? So we'd sort of shut dev off overnight, fire it up in the morning, and there'd be hundreds of events come through in the matter of like within a minute, say. And Lambda, because it's elastic and fantastic, would just fan out and overwhelm the API with all these requests. Now the API was PHP, not my tech choice, but single-threaded, synchronous, so it couldn't handle all this load. And it sort of raised the question around what guarantees we have with Lambda, because it seemed that all of the events came through, so that's great, there's no sort of missing data, but the Lambdas all failed, we got log data, there was no guarantee that it would eventually succeed or something. So the state of our monitoring tool drifted from AWS. No good. So what we need is sort of constrained concurrency. We want to make sure that these Lambda all fire, but they only fire sort of 1 or 2 or 3 or however many we want at a time. We want some automatic retry when things fail. We need to be alarmed on failure, which is actually pretty simple. And we want to reconcile drift, because no doubt, despite how hard we try to solve all these problems, at some point something's going to drift, and we need to make sure that's remediated eventually. So that's probably the easiest problem to solve, actually, just using our scheduled batch sync solution, our option 2. So we can just regress to running that script once a night, and it will catch any errors that happened during the day. But we can limit the throughput to make sure it's kind of just doing 1 or 2 hosts at a time, and it's not putting undue load on the system, because time is no longer an issue. So we can reuse all the code that we use for our event-based Lambda, and that's about the sum of that one. So we needed alarms on failure was a problem we need to solve. Really easy. We're logging to CloudWatch. The Lambdas are being triggered, so we can create a CloudWatch rule to fire whenever we encounter one of those log messages. More difficult problem to solve is the constrained concurrency. So there's 2 real options here. We can create some sort of global lock or semaphore so that when all these Lambdas fire, they contend for that lock and sort of sequence themselves. Or we're hoping to find even simpler is like an AWS queuing service that has that intrinsically built into it. So we just send something to a queue and we say, do all this work, and that happens by default. Also, that's going to hopefully simplify our retry back-off logic by having that as a feature built in as well. So I'm sort of coming up on time, so I'm just going to quickly go through the bad options. We tried to use SQSQ. SQS is a queuing system, best effort ordering, etc. Check it out. Unfortunately, the problem with this solution is that there is no way to trigger a Lambda from SQS. So we can put these events into SQS, and they queue up, and they never get actioned. So we could solve that by creating a CloudWatch cron job, like a scheduled job in CloudWatch that fires every 1 minute. So at least our delay now is only every 1 minute. We fire up a Lambda, it flushes out that queue, everything's back in sync, but all sorts of problems here, right? Most of those operations are going to no-op, so we're running that 3,600 times a day, and really there's only 3 or 4 changes a day, so it's a big waste of resource. It's added complexity. I think you guys get it. We could add an SNS topic, so SNS, Simple Notification Service, has great pub/sub sort of primitives that lets us fan out a message, so we could fan out both to the SQS queue and to Lambda, so Lambda would be triggered to say, hey, something's happened, go and have a look at the queue. Again, additional complexity. And also there's no guaranteed delivery with SNS, so chances are messages might go missing. So the solution that we landed on was serializing via Kinesis streams. So AWS Kinesis streams are persistent sharded streams of records. They call it a record each event. And the clients kind of maintain their own cursor to say where they're up to in that stream. And lastly, those records get cleaned up after some retention period. So there's a great opportunity for retry and back off and handling failure. Kinesis lets you configure when you build it shards. And basically the rule is that each shard can only have 1 consumer at a time. And Lambda has built into it the ability to have its own consumer. So it comes as a service to you. You just say, I want Lambda to listen to each shard, and those are completely serialized, right? So they'll only ever process 1 event at a time in that stream. And we've solved our concurrency problem. If we have 1 shard, we'll only ever have 1 Lambda firing at a time, and we can have 2 or 3, however many we like to keep our PHP API happy. It does have guaranteed delivery once it lands into Kinesis, and you know, there's some limit to that because of the retention policy. It's got built-in retry, so if your Lambda fails because of some environmental issue, it'll come back and try later. The only downside to this that we sort of encountered is the fact that errors are blocking. And what I mean by that is if a Lambda fails to process an event, it'll try again and it won't move the cursor. So it'll try that same event next time. And if it's like an ongoing error, if it's a code issue that's never going to be solved, then it's just going to stay on that forever and you're never going to move forward. So it's really important to make sure you're aware of that when you're writing your error handling. So to build this out, we publish the function, we create the Kinesis stream, we create an event mapping from the stream to the Lambda function, create our CloudWatch rule to listen for EC2 events, we create an EC2 event source, and we add Kinesis stream as the target, so we're lining up all the ducks, and Terraform is going to make that easier for you. Now our Lambda is going to be given different data now. It's not going to be given EC2 events, it's going to be given a Lambda stream. So they look a little bit different. It's an array of Kinesis records, and the data in each record is like base 64 encoded JSON. So that's easy to solve with this sneaky little function, which is just going to wrap the handler that we were using for EC2, because that data's still in there, right? We're just going to wrap it with this that says for each record, I'm going to extract that record, decode the base 64, and then pass it to the EC2 handler, which is already aware of how to take that instance ID and that the state and update the Zabbix API. So we had problems with, make sure that you consider failing silently, right? If you encounter an API call that just keeps failing, you've got to drop it silently, maybe move it to a different queue somewhere else for like human intervention, fire some alarms. So also you might end up with instant state being out of date. If there are errors, that stream's going to fail to process quickly, and you're going to end up with machines that said they're booted at the time of the event but have now since been shut down. So essentially when you run your Lambda, don't trust the event that comes in because it could be stale. Query the EC2 API, get the latest state for the machine. And that's the gist of Kinesis. Some final thoughts, but thank you very much for your time, everyone. I hope that's helpful to you somehow, and I'll welcome questions. Yeah, totally. So we had a monolith for ops code, so like all the engineering code wasn't, or the dev code wasn't in there, but so all of our Terraform scripts were in there, and for each Lambda, we'd often have multiple Lambdas in a single file because you can just define different Lambda functions with different entry points. But we would create a make file that would like take that, grab the dependencies, zip it up, ship it to AWS. Yeah, great question. I can tell you the Lambda cost nothing because we were well below the 1 million invocations per month limit. The Kinesis, I couldn't tell you with confidence. I would say it was on the order of cents or dollars though. It wasn't a line item in my budget. Thanks everyone.